To the viewers, the students, I would like to once again remind you that I expect that you are trying out the numbers we always leave you, me and my other colleagues that are facilitating in this program. And please, in case you're not able to get the answers that we normally give, we encourage you to get back to us through our available contacts. I will begin by giving you my email address today. I do conduct and answer your questions on Facebook, on my Facebook address, and you can send any queries on that address. Now, we were looking at connected bodies, and without wasting time, if we can flash back quickly for the purposes of picking up from where we stopped. We had our diagram, which I worked through towards the end of our previous lesson. I am going to go through it, but this time round, assume that I have masses, M1 kilograms, and mass M2 kilograms. We are, in this case, going to assume that M1 is greater than M2. If M1 is greater than M2, it implies M1 is going to exert a weight here of M1G, and M2 is going to exert a weight down. But since M1 is greater than MT, it means it's the heavier mass. If you release these masses, the motion will move in that direction. As M1 goes down, M2 will go up. Incidentally, the two will move with the same acceleration, and once you release them, a tension will develop in both sides of the string. We are having one string attaching the two bodies. That's why we say they move with the same acceleration. We were looking at application of laws of motion. So if we use the second law of motion, we obtain this expression. And if I consider the mass M1 kilogram and I apply this expression, the M1G, which is the weight, or which you can call a force now, minus the force that will develop in the string, the tension, in equilibrium, should be equal to the mass, which is M1 times the acceleration. If we look at the second mass, M2G kilograms, as this goes down, remember this is going up. So in this case, T is greater than mg. So our T, which is the tension, minus the weight there should be equal to M2 times the acceleration. I'm deriving a general expression. Last time, we simply applied that expression because the lesson was coming to the end, and I wanted to leave you with information to ponder on our next lesson, which is now. If we add these expressions, we shall obtain left-hand side, M1G, minus T, plus, that is the first part, plus the first part of the left-hand side of the other part, T minus M2G, will give us the right-hand side added together, that is M1A plus M2A. T here is an additive inverse, so it will cancel out, and G is a common factor. So if we pull out that common factor, we shall get M1 minus M2 being equivalent to, we pull out A here, you will all notice that A is also a common factor here, this bit of factorization, and we shall have M1 plus M2. My interest is to find the acceleration, remember? So our acceleration made as a subject, I will skip a step of dividing both sides and write that if I divided by M1 here and M1 there, our acceleration will be M1 minus M2 over M1 plus M2 times the G up here. This would be the acceleration. if units are known, the SI units for acceleration will be meters per square second. This question usually requires the candidate to find the tension and find the corresponding acceleration. We have got the acceleration, so in order for us to find the tension, we are going to use one of these two equations. We are going to use one of these two equations, and ideally, I would like to mention this today, that most students usually find challenges with dealing with negatives or integers, what we call integers, but especially the negative ones. So if you can appropriately see equation 2 and compare it with equation 1, it is easier to make t the subject in equation 1, in equation 2, than in equation 1. So if we make t the subject, which is a concept that is again taught to our ordinary level students, our t, which is the tension, will actually be equal to m2a, which is already at the right-hand side, plus this one, when it crosses the equal signs, will become a positive, plus m2g. Notice that our m is constant, so I can factor it out and stay with a plus g. Now I have already got an expression of a, which appears to be a big expression, but I'll fit it in here to get the tension. My t, therefore, will be equal to m2 into, when I fit in the a, what I want to show you here, this a also has a g, which is also available here. It means that the g will now become a common factor. The g will now become a common factor. So that g will move out. I can bring it out early. And that means that since I have brought it out, I have a 1 here. So I'll have my a, which is now m1 minus m2, out of m1 plus m2 plus 1. Because I already took this g out. And I have taken this g, which should have been part of this, out. So what is left is simplifying this. This one can fit here. I will have my LCM in here will be m1 plus m2. So my factored term out of the bracket, maybe I can come back this side so that we don't squeeze things here, yet we are here to ensure that the learners follow. My t will therefore be m2g into, the numerator for the first term will stay the way it is, but when I divide this term by my LCM, which is m1 plus m2, it will be m1 plus m2. And I will pick my LCM back there, and then I can now simplify. This m2 will cancel there, and my tension, as we can see, this is m1 plus m2, m1 plus m1. That one gives us 2m1. So I will have a 2 times m1, which is inside here, times this outside common term out of the sum of m1 plus m2, and this will now be the force. This will be the force. Now, these numbers will require sometimes the candidate to find what we call the reaction. If we can study the pulley diagram that I drew at the start, I have the strings. I will just put a cross section. These strings have a tension, each of them, and here where the pulley is hinged, there will be another tension which we will call the reaction. If they tell you to find the reaction, we will use the condition of equilibrium, that in equilibrium, forces acting in opposite directions are equal, and therefore R will be equal to T plus T in this case, and therefore the reaction will be equal to twice the tension. And since we know the tension, if they want the reaction, you can always use that expression and get the reaction sorted out. Now, quickly, we will try out one more number. I know last time we did one using that formula, assuming that I have two masses, one for 3 kilograms and one for 5 kilograms, and they want me to find the acceleration and the tension. The tension, we can choose to call it T1, and the acceleration will now be that it will always take direction in the direction where we have the greater force acting. The weight here is 5G. The weight there is 3G. At that stage, we have indicated all the forces acting on our diagram, and we are saying this will go down as this goes up with the same acceleration. So 5G minus T will be equal to 5A. I hope you are able to see this. And then T minus 3G will be equal to 3A. Incidentally, when we apply figures, the working is so brief that you don't need to occupy the whole of that space. If I add these directly, I'll get 2G. You can actually choose to add like this. That this T will cancel, and this 5 minus 3 will be 2G, and this will give us 8A. And from here, our A can be G out of 4 meters per second squared. Our A can be G out of 4 meters per second squared. If G is given, like it will always be the case, then G can be substituted, and we would get our acceleration as 9.8 divided by 4, which should give you 2. You can use your calculators. After getting the acceleration, I will leave it in G form. I can now get the tension using, again, the second equation. Tension will be 3 into A plus G. This time you will notice that this was our A expression, but here the A is so simplified. It is G out of 4. So the tension will actually be 3 into G out of 4 plus G. Again, if you are comparing it with the way we got the tension there, you clearly see that the G will come out. So I'll have 3G into 1 plus a quarter. For our little children, the primary students, and even the O-level students, and even the A-level students, this bracketed term is an addition. It can be a complete number in primary, where they say add. The answer is simply 1 and 1/4. If they are not giving marks for working, you simply join them and produce an answer in a mixed fraction form. So if we use that, we'll have our 3G times 1 and 1/4 is actually 5 out of 4. And this will give us 15G out of 4 newtons. Again, you can substitute in the value of G to get the numerical value of the tension. Now, that information should be enough to enable students to work out numbers that involve two particles that are connected together with a string. The string must be inextensible, and the two particles must be connected using a pulley over which the string that is actually connecting them will pass. We shall move. I'll request the producer to show the question on case 2. That was case 1. There are several cases of connected bodies. Case 2 has a question that looks at connected bodies. I remember talking about trailers. Trailers, our dear viewers, I'm sure you're able to read and capture. I request that you capture that question that we are going to work through. It looks at a trailer. A trailer has several parts that I have described here as wagons. And these wagons, of course, I am going to, for the purposes of illustration, assume that, of course, they have tires, which are normally metallic. And then there is an initial part of that trailer where I don't know whether they call them pilots also or captains, where they sit. Now, this one has several wagons, and their total mass is 10 tons. A ton is equivalent to 1,000 kilograms. This is also technical. If a student does not know what a ton is equal to, then this number can become a problem to such a student. And the truck, which is actually pulling this, normally there is a connecting chain or a very strong rope that connects these two bodies. They have told us that this one has 50 tons. That is 50 times 10 to the power 3 kilograms. Our dear candidates, I encourage you to copy even where I put EER, because after I have done this number, you automatically qualify to try out the next number and you should be able to get it correct. I have the confidence that if you follow our working, that number should be history. The answers are attached in brackets. Now, what are we required to do? They are asking us to find the tractive force. Tractive force is similar to what most books will call the driving force. The driving force. For the parents who are following, of course our target are students, but if you are driving a car, the moment you step on an accelerator and the engine causes the car to move faster, the force that is actually causing the car to move, or the bicycle or the motorcycle, is what we call the driving force. It is derived from the engine force, and the more you step on the accelerator, normally the faster the car is expected to move, assuming other conditions are constant. So there is a force here, and the reason why we use two arrows, this arrow is ideally showing the force that is pulling that one, and this arrow is showing that if we are only considering the motion of this one, there should be a tension still that is trying to resist this motion because of the other body connected to the other side. So we are going to use Newton's laws of motion. They have told us that the two are moving with an acceleration of 1 out of 10, which in the question is written as 0.1. And they have told us we should ignore any resistances. In some instances, there would be a resistance here, as you will notice, and a resistance there. So in the case where there are resistances, I'm going to derive a general expression, which I will later use to do this number, so that it can help you in the next number, because there are cases where we have resistance, especially the last one. If I let the resistance here to be RT for the track, and the resistance here to be R wagon, then if I use F is equal to MA, I can consider the track alone, the track first. The general equation would be D, which I have called the driving force, minus the resistance RT for the R track, minus the tension that would be there, should be equal to the mass of the track, if I call it MT, times the acceleration. If I look at the wagon, I am deriving general expressions. The driving force, if we are only considering this, is similar to the tension. The tension minus the resistance, which I'm calling RW, W standing for the wagon, will be equivalent to the mass of the wagon times the acceleration. If I am going to generalize this into one equation, it is as good as adding these two expressions. Of course, this would be an equation, and this would be an independent equation. So if I consider them as one body, which would be similar to adding this, I would say D, I'm not going to add, I'm just getting it direct here, but I will explain. D minus, now I will take away this T here. Then I will add on this T here. Why? Because this T is in the direction of D, but this one is opposite. Then I will take away RT and take away RW, because they are acting in the opposite direction. That is, if the body is going the other side, the resistances are always acting in the opposite direction. Would be equal to the mass of the wagon plus the mass of the truck times the acceleration. If this is written at a go, that is what we would have. And you will notice that these tensions will cancel. So if I was to add, this and this would cancel, but these would be actually adding. They would be adding together. They are minus, minus, so they are adding. And these will still add to give us that. So the general expression is D minus RT minus RW is equal to MW plus MT into the acceleration. I am going to use this now, but for the next question, there is a part that will require you to use this expression that I have just derived. This is a general expression. Now, to suit it, to answer this question, I will simply substitute in. Remember, they have told us that there is no resistance. RT and RW are equal to 0. So the tractive force which we actually want is going to simply be equal to the sum of the masses times the acceleration. Our tractive force is therefore equal to 50 plus 10, all multiplied by 10 to the power 3, because they are all in tons, 50 tons plus 10 tons, then times the acceleration, which is 1 out of 10. My tractive force will therefore be 60 times 1,000 times 1 out of 10, and of course 1 0 will go, and our D will be 6,000 newtons. It is important to remind the candidates that you are expected to define the symbols you choose to use in your question, and that is why I'm saying D is the tractive force. RT, however, in mathematics, this emphasis of defining the symbols used may not be so much considered like we do in physics. So our expected answer is 6,000 newtons, as we see it in bracket there. And I would like to remind you that the next bolded question is an exercise for you. So we shall move to the next case, but not before we move that the last part of that question has some resistances. And these resistances are attached, as I have indicated here. The intention of using this approach was to enable you be able to get correctly all those three parts. Question 2. Question 2 is looking at another scenario here. Two masses, M1 capital, and M small and M big, are connected over a pulley, and this pulley is inclined at an angle. This is another case that is very important to look at. One mass is hanging. We have a pulley here. We have one mass on an incline connected to another mass by a string passing over a pulley. They are telling us that the capital mass is greater than the small mass. So we shall let this be the capital M and let this be the small m. The sketch is beginning to develop shape. I will attach the forces acting. Since this one is greater, we can now tell, my dear students, that the acceleration will be towards the direction of the heavier mass. That one you should know by now. 2, the moment they are allowed to move, the string or the rope connecting the two will develop tension. And the mass that is on an incline, since it is going to move along the plane, they are giving us the angle of this plane as 30 degrees. Since the small mass will move along the plane, then it implies that we will get the downward component, which I expect you still remember, mg the sine of. This time I'll put 30 degrees. And our intention here is to get the general expression for tension and acceleration for this system. And later there is a number that you're expected to try out, as you can see, the bolded number. Now, since motion is going there, we shall use F is equal to ma. For the m kilogram mass, that is the capital M, we have mg, which is the force, minus the tension. I have chosen to use T because it is still one rope. There are cases of more than one rope, as we will be able to see. My is equal to m capital A times acceleration, capital M times acceleration. If we consider the small mass, as this goes down, this goes up, that means the tension here is greater than this downward component. And the assumption here is that the incline is smooth. So we don't have any resistance or any friction there. That means that T minus mg, the sine of 30, should be equal to small m times A, and that will be equation 2. So the concept is almost the same, my dear students. If I add, adding 1 plus 2 will be able to give me left-hand side as mg minus m times a half. The sine of 30 using your calculator is a half, but again using this triangle, which is isosceles, you can tell from your trigonometry that if this is 30, sine is opposite over hypotenuse. Should be equal to now our capital M plus our small m times A. Since our intention is to get general expressions, it means we want to get the expression for A and get the expression for T. These m's are different, remember? They are different, but they have a common g. So if we factor out the g and take this as the LCM, I'll get 2 capital M minus small m all over 2 should be equal to capital M plus small m times A. And finally, I can get my acceleration. I'll fit it right here. I can get my acceleration expression as 2m minus small m into g over 2 into m plus small m. That will be the acceleration. We divide through by m plus small m. And then we can back substitute the acceleration into one of those expressions to get the expression for tension. We can back substitute to get the expression for tension. Using equation 2, tension becomes small m plus, again, small m, g over 2. When this crosses the other side, we add, and this small m has A. If I substitute for A, which we have got as the whole of that expression, the small m will come out. It is common, and I will have my A, which is 2m minus small m into g over 2 into m plus m minus m half. The m here moved out. It is this one. So minus g out of 2. When this m moves out, which is here, I stay with A. So the whole of this is that A we got. And here I stay with g over 2. So if I take the LCM and simplify, I'll get 2 into capital M plus small m as my LCM. Definitely when we divide it here, it goes in by 1. So it is not going to change. My small m out, I will have 2m minus m. I'm going to pull out the g also. This g we can all see is common. So my common term becomes mg out. When I divide this here, the 2 will cancel. So I'll take away my m plus small m. It is important that we follow the algebra very well. I expect that we have got this sketch. I want to create space. To create this space, I am now going to look at opening this bracket. If I open this bracket, the capital M will be negative and the small m will be negative. That means the capital 2m will decrease by 1 if we take away that one, and this will increase to minus 2m. So I can finally say that my tension expression will give me m minus 2m to small m times the mg. There is an mg out. Our tension will be mg small m over the LCM, 2 into big M plus small m. This will be our tension expression. The final tension expression would be given by this of course, in newtons. Now, the bolded question is saying, what would the acceleration and the tension be if you repeated this very diagram, but you change masses now? You attach 3 and 4 as the masses. If you repeated this, I will simply work through 1 to see, are the answers given in brackets correct? Oh, have we got the correct expression? If our expression for acceleration is 2 capital M minus small m times g out of 2 into capital M plus small m, and we are saying the capital M is 4 kilograms and the small m is 3 kilograms, according to the exercise you are expected to try out, and the angle is 30 degrees. The angle is 30 degrees. Since the angle is 30, we are in agreement because we had used 30, so the expression we have is embracing that angle. It is not changing. So if it is not changing, we want to be sure and see. 2 times 4 minus 3, I'm substituting. My m is 4, my small m is 3, times g, we shall put in g later, over 2 into 4 plus 3. What do we get? 2 times 4 is 8, minus 3 is 5. So we have 5g out of 4 plus 3 is 7 times 2, 14. So our acceleration is 5. If we used 9.8, if we used 9.8, we should get an answer that is approximately equal to that. This will give us 45 plus 4, that is 49 out of 14. 49 out of 14, and if we put in by 7. Now, the reason I used that answer here, I considered this as 50, as 10. G can be considered as 10 if you round off. So assuming that we use G as 10, we have actually 50 out of 14, and if we take it through by 2, we have 25 out of 7 meters per second squared. If we use 9.8, we would have 49 as you've seen out of 14, and by 7 we would have what? By 2. Okay, by 7 here. We would have 2, and by 7 we would have 7. On average, this gives 3.5. And this, if it is rounded off, 25, 7 goes there 3 times, 21, you remain with 4, and it will go in around 6 times, around 5 times again. So 5, you remain with, you get 35, you remain with around, so approximately the answers are supposed to be the same. That's why we usually use 9.8 at A level, but at O level we use G as this, because they are ideally meant to give us an answer that is approximately the same. So now that we have tested our expression and we are getting the correct answers, I think our dear candidates, you will be able to try out that number to get the tension. We can move on to the next case. And that is case 3. 2 masses connected with a small mass on a tabletop connected to, yes. This is a tabletop. We sketch our table like this. There are many cases, remember, and now that the concept is the same, I may not complete this. I will interpret it and then go to another case because our time is fast running, as you're aware. We again use masses M1 and M2, and in this case, we still want to find a general expression, and there is an exercise that you should capture in advance. The capital mass is here, and the smaller mass is there. Because it is a tabletop, this mass will exert a weight, as we saw in our first lesson, that masses are placed on a level will exert a weight downwards, but they will have a reaction, a normal reaction that I can call N, and the tensions will still be the same. Why? Because the rope is the same. And there is a reaction here which we shall find out. This ideally is expected to be 90 degrees at this point. So the weight is mg. So using acceleration following that way and this way, for the capital M kilogram mass, our mg should be equal to, mg minus T should be equal to ma. And for the small m kilogram mass, it is on a tabletop, so it is going to move, but there is no other force this side if we assume there is no friction. It is not rough. So our tension minus what would be the resistance should be equal to small ma, but there is no resistance. So the tension is actually equal to the mass times acceleration. Adding these two equations will give us mg minus T plus T is equal to big M plus small m times A. And this will cancel, giving us our acceleration as big mg out of mass, total mass, m plus small m, meters per second squared. To find the tension, we simply substitute in now equation 2, which is the most suitable equation, because it doesn't have anything to do with subtraction even. So if we substitute for T here, for A, our tension for this kind of arrangement will be small mass times the acceleration, which is capital mg out of the sum of the masses. And our tension would be given by mg out of m plus small m newtons. Our dear candidates, that is another case. We are going to look at another case. These two expressions can help you to work through that exercise. There, if the masses are 2 and 3, I could quickly say, if they were 2 and 3, the 3 would be here, and the 2 and 3 would give us 5 as the sum. And if we take, again, g as 10, you will notice that we would get the acceleration as 6, which is actually given as one of the answers there. So you can, again, use this information to find the tension, the acceleration. I've given you a quick hint. This topic is a very important topic, and our dear candidates, we are going to look at another case. This case is still a table, but now we have 3 masses. But there is one thing that I have remembered I have not shown you there, which I can quickly flash back and show you. That at this point here where we have the pulley, we have a 90-degree arrangement. That if we have this as tension and this as tension, then the reaction on the hinge here, if we call it R, is actually, you can opposite the reaction this side, and we can get it by taking the Pythagoras theorem here. That this followed by this should be able to give us this. Remember, the vector equation must be correct. That if I look at this followed by this, I should get the resultant. So the resultant should be equal to T squared plus T squared, and that resultant there, the resultant, their side would be 2T squared, and therefore the resultant will be T, the square root of 2 newtons. If they ask it to find the reaction, it is not the resultant, but the reaction at the hinge, it would be given by this. Here we have 3 masses. M1 is smaller, the weight will be that, M2, and then M3. Those would be the weights now, M3G. Now these are 2 ropes. There is this one, and they don't join at all. Therefore, their tensions are meant to be separated. If we let this be T1, then we'll let the tension here to be T2. And we shall repeat the same approach. There will be a reaction here, and this would exert a weight, which is M2G, if it were to move vertically. But if the motion is horizontal, the reaction can only be used at a point where we probably are interested in getting the reaction at that point. So this we'll move there because they have told us that M3 is greater than M1. So this will be the direction of motion. As M3 goes up, goes down, M2 goes that side, and M1 goes up. Quick equations, M3 kilogram mass will give us M3 G minus T2 being equal to M3 times the acceleration. M2 kilogram mass, this one will be acted on by the two tensions. So its motion will depend on T2 minus T1 being equal to M2A only if this surface is smooth. If it is rough, there will be a frictional resistance here, which can be used here. If it is rough and there is a resistance, this resistance is given normally as a coefficient of friction times the normal reaction. And in equilibrium, this reaction, which I've called N, is actually directly equal to the weight at that point. That is another scenario. The M1 kilogram, which is going up, the tension here will be greater than the tension on the other side. And the tension there is T1 minus the weight is equal to M1A, equation 3. At high school, the students are prepared to know how to solve an equation with three unknowns. Here we have three unknowns. We have A, we have T1, and we have T2. That's why we have three equations. But the easiest way to solve this particular type of equation is to add all of them at a go. Add 1 plus 2 plus 3 at a go. That is the beauty with this one. It is different from the row reduction by echelon method that is used in paper 1. So if we add all of them at a go, I'll have M3G minus T2. I hope you can see I'm adding the left-hand side first. Plus T2 minus T1 plus T1 minus M1G. That is the left-hand side. Should be equal to, I'll add the right-hand side also. M1 plus M2 plus M3 times A. I've factored out the A. You will notice that since our intention is to get A first, all these will cancel. The tensions will cancel. The negative T2 cancels with T2 positive, negative T1 cancels with that. So we end up staying with M3 minus M1 into G being equal to A into the sum of the masses on the other side. And from here, we automatically get our acceleration as the difference between the masses. Those are the masses that are actually moving over the M1 plus M2 plus M3. And this would be newtons per meter per square second. This gives us the acceleration expression. To find the tension, we can choose either to use equation 1, that one will give us T2, and then we use equation 3. Equation 1 will give us T2. I'm not going to do it up to the end, but T2 would be ideally M3 minus M3 into G minus A. Because this T2 will cross and come here, and this one will go there. When it crosses, it becomes positive. That's why I'm writing it positive, but on the left-hand side. And then when this crosses, the M3 is common. It's the same mass, same denominations. It's also capital M. And G will be, we will subtract A there. Since we know the value of A, when you substitute and simplify, you should be able to get T2. Again, from 3 to get T1, would cross this one. And M1 will be common, A plus G. We substitute again for A here, and we simplify. Your paper 1 mathematics should be able to enable you to simplify these as you have seen from the others. This question can be brought the way it appears, and they say, derive the expression for acceleration. They can say, derive the expression for tension, or find the tensions. There is an attached example there, no exercise, that you're expected to do. We can attempt to look at our next case. Our next case is case 5. And case 5 is looking at, you see that diagram there. I chose to use case 5 to look at a diagram which is incomplete. I am going to complete it from here. We have a double incline. There is even another case in this category. We have a mass, we have 2 pulleys here also. We have this rope connecting the 2 masses. We have another mass here, and we have another mass here. Even if I don't complete this, the concept should be clear to all of us by now that candidates should actually be saying, why doesn't he leave us to try out that one? By now, I expect you to be positively charged that you can take on any number. For this one, this is 1 kilogram, this is 2 kilograms, and this is 3 kilo. So the forces acting, we have a normal reaction. I can choose to call it N, and we have a 2G, which is the weight. Here, we have G, the sine of 45, and here we also have 3G, the sine of 45 degrees. We have tensions. This is a different rope. I can call this T1 and T1, and I can call this T2 and T2. If these were released, notice that they are inclined at the same. The bigger mass would dictate that the motion will go the other side. It will go in a clockwise direction. That means this one will move like that. This one will move like that. And that one will also move in that direction. So using our F is equal to ma again. If I look at the 3 kilogram mass, my expression now, again, one thing that I can also add is that they can set this question and there is friction. This side can be smooth, and they say this side is rough. If this is smooth, no resistance here as this goes down, because friction opposes the direction of motion. So whenever they say there is friction, it acts in the opposite direction to the direction of motion. So with the 3 kilogram mass, we have 3G, the sine of 45, minus T1 is equal to 3A. But sine 45 on your calculators is 1 out of root 2. So I'll substitute it wherever it will appear. And 1 out of root 2 minus T1 is equal to 3A, equation 1. For the 2 kg mass, it is on a horizontal table, and the forces acting once again are the tensions. So it is T1 minus T2 will be equal to the mass, which is 2A. That is, again, if they don't mention any resistance there. And then for the 1 kilogram mass, it is going up. So the T2 minus G times 1 out of root 2 should be equal to 1A, or just A. Now, as we move towards the end of our lesson, I want to say, whenever there are 3 equations, simply add them. Simply add them, and when we add, we shall have 3G root 2 over 2 plus minus T1 plus T1 minus T2 plus T2 minus G root 2 over 2 is equal to, when we add all these, we shall get 6A. The tensions will cancel, and this will give us 2G root 2 out of 2 being equal to 6A. Notice that 1 out of root 2, if we rationalize it, it will give us the root 2 out of 2. That's why I've substituted that. These 2 will cancel, and the acceleration will be G out of 6 root 2 meters per second squared. If you back substitute, you can get T1 and T2 respectively in the different numbers. I would like to request the producer to move down so that candidates out there can capture their numbers. I don't know how you'll do it. There is an exercise in the footer area, because I didn't want to go more than one page, there are some numbers in the footer that I would wish these candidates to capture to keep them moving. Yes, my dear candidates, I want to focus your attention to the footer. I have quoted two textbooks. There is Understanding Mechanics by Sadra and Soning, and Mechanics and Probability by Bostock and Chandra. There are several textbooks. Go to exercise 3C. That is Understanding Mechanics. And then exercise 5C. It is by coincidence that they are all C's. And then I have also gone back to the question bank, and I've been able to pick just a handful of numbers that I expect you to try out. You are encouraged to look at the other years for more numbers. This is a common number, and I want to thank you so much. I want to thank the management of Telefina, BBS. I want to thank my producer. I want to thank the lady on camera for making this lesson happen. I wish you the best. Catch you when you see me here again. God bless you. Good day.
Wewa, tuenze nnyo tuenze Master Kakulu atera okuba nti abaana ongera okubagaza okubala sikwangu nnyo bantu bangi tebakwagala naye ate bw'oba osomesa bangi abaatulaga nti weewaawo bagoberera era ensonga abazitunulira bulungi nnyo nga bulijjo tubategeeza nti okubala bintu bino ebirimu okubala kabeere physics okwegezaamu okufuna enamba zibabawo ezo naawe n'ogiddamu n'olaba nti osobola okubala obulungi kyekimu ku bigenda okuyamba naye bw'onooba nga mu kirasi wano wokoma n'otegezaamu gwe ng'omuntu kiyinza okubeera ekizibu nnyo okugoberera n'okusobola okuba nti otambula bulungi ne kirasi zaffe ezo na bulijjo naye nga bulijjo okuva ku ssaawa 3 paka ssaawa 4 tuba ne P7 okuva ku ssaawa 4 paka ku ssaawa ate 5 tuba ne kirasi eya senior 4 ate kuva ku ssaawa 9 paka ku ssaawa 10 ne tuba ne kirasi eya senior y'omukaaga nga gye tubaddemu ku ssaawa eno nyongera okutegeeza nti essomero lirina okuba nga ogoberera ly'essomero lya Green Hill Academy bali wano Kibuli ate era ne Buwaate ate mu ngeri emu ne Maryland High School essomero liri Ntebe eryo lya secondary ate era nyongera okutegeeza nti big ye peni gy'olina okuba nga okozesa te university mwolina okutwala omwana wo y'Enkumba University olunaku wali okusoma kukomye wano tujja kuba tudingana ate olunaku olw'enkya sigala ng'olaba telefayini yaffe round about ndowooza iddako tovaawo ayi Katonda kuuma maaso mogi.
Somera mu ddiiro lyo ng'ewagiddwa Maryland High School erisangibwa Entebbe. Ssomero ly'abawala n'abalenzi tusomesa arts ne sciences okuviira ddala ku siniya esooka okutuukira ddala ku siniya ey'omukaaga nga lisangibwa mu kifo ekiweweevu obulungi. Tulina ebisuula eby'omulembe, science laboratory ssaako ne computer lab wamu ne.
She gives you her number, but your pen didn't work and the bus is gone. Get a pen you can rely on. Big Crystal, the long-lasting pen with perfect ink flow.
Wamune.
Green Hill Academy has high standards of learning and the teachers are very good. They give you a sense of belonging.
Green Hill has helped me to discover my talent.
The environment is good.
Encouraged us children to be excellent.